Have you ever clicked a button, scroll through a feed, or maybe tried to log into an app and just, well, expected it to work perfectly?
Happens all the time.
Right. And then what about that moment when it doesn't? That little jolt of frustration. Today, we're kind of pulling back the curtain on a crucial, but often pretty invisible world behind the software you use every single day.
Yeah, it's something most people don't think about until it breaks.
Exactly. We're diving deep into how we actually make sure a program does what it's supposed to.
That's right. Our deep dive today is all about functional testing. Think of it as the foundational check.
Foundational check.
Yeah, the core validation that ensures software performs exactly as its requirements say it should. It's really about building trust in these digital tools we rely on so much.
And for this journey, we've sourced a really comprehensive guide. It's actually a set of interview questions and answers.
Which might sound a bit dry, maybe.
It might sound like dry technical prep, yeah, but it turns out it's an incredibly structured and honestly insightful way to unpack this whole topic. It's helped us distill the really important nuggets for you.
Absolutely. Our mission here is to take what might seem like, super specific technical knowledge and transform it into something surprisingly accessible and fully genuinely valuable insights. We'll be exploring the essential concepts, some of the subtle nuances, and definitely the practical applications of functional testing.
So look, whether you're building software yourself or you're just an avid user, maybe you're just curious about how this digital world actually hums along.
Which is fascinating in itself.
It really is. Consider this your shortcut to being genuinely well-informed. Let's start unpacking. Where do we begin?
Okay, so at its core, functional testing is defined as a software testing method that validates a system against its functional requirements or specifications.
Right. So functional requirements.
Right.
What does that actually mean in plain English?
It means checking if the software fulfills the specific tasks it was designed for. Things like processing a payment correctly or saving a document when you hit save.
Gotcha. So it's not just hitting save and kind of hoping for the best.
Not at all.
It's hitting save and then verifying the document actually saved
Yeah.
in the right place with the right content.
Precisely. It's about providing specific input and then checking that the output matches exactly what was expected based on those requirements.
Okay.
And a really crucial aspect here is that functional testing is what we call a black box method.
Black box. Okay, what's that?
It just means the testers aren't concerned with the application's internal source code. They don't need to know how it's built underneath. Their focus is entirely on the external behavior, what the user actually sees and interacts with. Does it work from the outside?
That's a really key distinction. So if you're not looking at the code, what are you looking at?
Well, you're examining the user interface, the UI. You're checking APIs, database interactions, client-server communication.
Basically everything the user touches or relies on.
Exactly, all the different functionalities. And it's worth remembering this can be done manually by a person clicking through.
Right.
Or it can be done using automated scripts.
Which touches on why this is so critical.
Right.
Functional testing isn't just some formality.
Oh, not at all. It's essential for validating those mainline functions, the absolute core purpose of the application.
Okay.
It also covers basic usability, making sure users can actually navigate screens easily. It tests accessibility.
That's increasingly
Hugely. And maybe most importantly, it tests error conditions. What happens when things go wrong? Does it give you a helpful error message or does it just crash?
That's a big one. Okay. Maybe an analogy could help make this stick.
Yeah, analogies are good.
Okay, imagine you've just bought a fancy new smart oven. Super high tech.
Right.
Functional testing is like going through that user manual, pushing every single button, the bake setting, the roast function, the self-clean cycle.
Making sure each one does what it says on the tin.
Exactly. To ensure each feature works precisely as advertised. You're not checking the wiring inside or the circuits.
Nope, that's not your concern in functional testing.
You're just verifying that if you set it to, say, 350 degrees, it actually gets to 350 degrees and maybe beeps when it's ready. You're testing the promise.
That's a perfect way to put it, testing the promise. And to test those promises systematically, there's a very deliberate, methodical path. It's definitely not just random button pushing.
Right, it's structured.
It involves a structured 6-step process, generally speaking.
6 steps. Okay, walk us through them. What's step 1?
First, you start by deeply studying the user requirements, or maybe the organization's requirements, and crucially, clarifying any doubts or ambiguities. You need to know exactly what it's supposed to do.
Makes sense. Get everyone on the same page. Then what?
Then, armed with that clear understanding, you design your test cases. These are the specific scenarios you'll actually run.
Like, user logs in with correct password, user tries wrong password.
Exactly like that, trying to cover all the angles described in the requirements. Step 3 then involves identifying all the necessary test data for input.
So the actual usernames, passwords, maybe product IDs, whatever you need to feed into the system.
Precisely. The specific values or information. Following that, step 4, you determine the expected output. This is vital.
Okay, so what should happen?
Yeah, what should the system do given your specific input and its intended functionality? You need to define success up front.
Right. And then step 5 must be running the tests.
Step 5 is the execution phase. Yep. You run all those carefully designed test cases.
And finally, step 6.
You compare the actual outcome, what really happened, with that expected output you defined earlier.
Ah, the moment of truth.
Kind of. This comparison tells you about the system's defect rate, its accuracy. It gives you a clear picture of its quality. It's the systematic nature that ensures you get thorough coverage, or at least as thorough as practically possible.
That methodical approach really highlights something important. The difference between functional testing and non-functional testing.
Yes, that's a fundamental distinction. Both are absolutely indispensable for a quality software product, but they answer different kinds of questions.
Okay, so lay it out for us. What's the key difference?
Well, functional testing is typically performed before non-functional testing. It's based entirely on customer requirements, the specs,
Right.
and it validates the application's core behavior. Basically, functional testing describes what the product does. Does it perform the functions it was built for?
Okay, what it does. So non-functional is?
Non-functional testing usually comes after. It
Right.
focuses more on customer expectations around quality attributes. Things like performance, usability, reliability.
Ah, so like how fast it does it or
Uh,
how easy it is to use.
Exactly. It validates those aspects. Non-functional testing describes how the product works, its characteristics, not just if it works.
Okay, let's try that car analogy again. Functional testing is checking. Does the engine start? Does the steering wheel actually turn the wheels? Do the brakes stop the car?
The basic operations, yes. The what it does.
Got it. And non-functional testing would
Yeah.
be checking its fuel efficiency, how quickly it goes from 0 to 60.
The smoothness of the ride, maybe. The noise level, how comfortable the seats are, that's how it performs.
Okay, that makes sense.
Yeah.
It's quality characteristics beyond just the basic function, both vital, like you said, but they have a different focus.
Exactly.
All right, so now we understand what functional testing is, why it matters, and how it differs from non-functional. Let's talk about the tools and techniques testers actually use. You mentioned it's not just random clicking.
Definitely not. There's a whole toolbox. One really fundamental tool is something called a traceability matrix, or RTM.
Traceability matrix sounds official.
It is pretty important. Basically, it's a document, often a spreadsheet, that maps your test cases directly back to specific requirements.
Ah, so it links the what we test to the why we test it.
Precisely. Its value isn't just in making the link. It gives you clear visibility. It helps testers track requirement coverage through the whole process.
As you can see, have we tested a requirement 1.2 yet? Yes, with these 3 test cases.
Exactly. It ensures nothing gets overlooked, that every piece of required functionality has at least one test case associated with it.
Smart. Okay, what else is in the toolbox? I've heard terms like equivalence partitioning.
Yes, equivalence partitioning and boundary value analysis often go hand in hand. They're both black box techniques.
Okay.
Equivalence partitioning is about being efficient. It divides the possible input data into classes or groups partitions where the system is expected to behave similarly for all inputs within that group.
So instead of testing every single number from 1 to 1,000.
Right, which could be impossible or just tedious. You pick one representative value from valid partitions, like maybe 500, one from invalid partitions below, like 0 or -10, and one from invalid partitions above, like 1001.
Ah, so it reduces the number of test cases needed quite drastically.
Hugely. While still aiming for maximum requirement coverage, it's about working smarter.
Okay, and boundary value analysis. You said they go together.
BVA takes that partitioning idea and focuses specifically on the edges or boundaries of those partitions.
Why the edges?
Because experience and statistics show that errors are much more likely to occur right at these boundary points. The minimum value, the maximum value, just inside, just outside.
Ah, So if a field accepts numbers from 1 to 100, you'd test.
You'd definitely test 1 in 100, but you'd also test 0 just below the boundary and 101 just above, and maybe 2 and 99 just inside, plus a typical value like 50 from the middle.
That's where you find those sneaky off by 1 errors and things.
Exactly. It's a very effective technique for finding bugs efficiently.
Interesting. Okay, we also sometimes hear about ad hoc testing, random testing, monkey testing. These sound less structured.
They are definitely less structured. Think of these as more exploratory, sometimes even chaotic approaches. Ad hoc testing is pretty much what it sounds like. A tester just explores parts of the application without a strict plan or script, using their intuition and experience to find potential issues.
Just poking around.
Kind of, yeah. Random testing might involve using tools to generate random inputs or data to see how the system handles unexpected stuff.
And monkey testing. That sounds fun.
Huh. It can be. It often involves truly random, almost chaotic input, like banging on the keyboard or feeding it junk data, specifically trying to crash the system or expose really unexpected behaviors.
So they're like stress tests in a way, trying to break it.
Sometimes, yeah. They can be surprisingly effective at finding edge cases or stability issues that very structured formal test cases might actually miss.
Right, because formal cases follow the rules. These break them.
Exactly. Another crucial pair of concepts for robust software is positive and negative testing.
Okay, positive and negative sounds like good path, bad path.
Pretty much. Positive testing involves providing valid input and expecting a specific successful action to occur.
Like logging in with the correct username and password.
Perfect example. You expect to get logged in successfully.
And negative testing.
That's the opposite.
Yeah.
You intentionally use invalid input, a wrong password, maybe text in a number field, data that shouldn't work.
And what are you expecting then?
You expect the application to handle the error gracefully. It shouldn't crash. It should ideally display a helpful error message like invalid password or please enter a number.
Ah, okay. So you're testing the error handling.
Exactly. And both positive and negative tests are absolutely vital. You need to know the software works when it should and that it doesn't fall apart when it shouldn't.
Makes total sense. Now, there's one more technique that sounded really intriguing. Mutation testing. That sounds kind of sci-fi.
Huh, a little maybe. It has a really interesting, almost meta purpose. It's not really about finding bugs in the application directly.
Oh, what's it for then?
It's about verifying the quality and usefulness of your existing test suite, your test cases, and test data.
How on earth do you test your tests?
Well, you deliberately introduce small, specific bugs called mutations into the actual code. You change it to a bit or add one where you shouldn't. Tiny little intentional errors.
Okay, you're intentionally breaking the code slightly.
Exactly. Then you run your original test suite against this mutated code.
And if the tests pass?
If your tests pass, even with that known bug introduced, it means your test suite didn't detect the mutation. That tells you your tests aren't sensitive enough in that area. They failed to kill the mutant.
Whoa, so if your tests fail on the mutated code, that's actually a good thing.
That's the goal. A failing test means it successfully detected the deliberately inserted bug. It tells you your test case is effective at finding that type of fault. It's literally testing the quality of your test coverage.
That's fascinating, testing the tests themselves.
Hmm.
Okay, shifting gears a bit from specific techniques. Software testing isn't just one big blob, right? There are different levels.
That's right. It typically operates on a spectrum of test levels. Think of them as sequential stages that build on each other, each with a distinct focus and scope. There are generally 4 primary levels.
4 levels, okay. Level 1?
First, we have unit testing, sometimes called component testing or module testing. This is the smallest scale.
So testing tiny pieces.
Exactly. Testing individual functions, methods, classes, or modules in isolation to make sure each little piece works correctly on its own. Usually done by the developers themselves as they write the code.
Okay, makes sense. Build with good bricks. What's next?
Next comes integration testing. Here, you take those individual units or modules that have been tested,
The good bricks.
and you start combining them, logically grouping them together, and testing the interactions between them. Do they communicate properly? Does data flow correctly from one module to another?
Checking if the bricks fit together and the mortar holds.
Good analogy. Then, after integration, we move up to system testing.
Okay, the whole building now.
Pretty much. System testing validates the complete and fully integrated software product as a whole. This can really only begin once all the modules are in place and basically working together.
And what are you testing against here?
You're testing the entire system against the overall requirements, functional and sometimes non-functional too. Does the whole thing meet the specifications?
All right. Unit integration system.
Hmm.
What's the final level?
The final level is acceptance testing, often called user acceptance testing or UAT.
Ah, the users get involved.
Yes. This is the crucial stage performed by the actual end users, the client, or stakeholders. It's their chance to verify and formally accept the system before it goes live into production.
So they're checking if it actually meets their business needs. Does it solve the problem they wanted solved?
Exactly. Does it meet the agreed-upon criteria for delivery? It's basically the final quality gate, the sign-off before deployment.
That makes a lot of sense as a progression. Build it right, piece by piece, then make sure the customer agrees it's right.
That's the ideal flow.
Now, beyond those main levels, I know there are other specific types of tests people talk about, like smoke testing. What's that?
Smoke testing is a really common one. Think of it as a quick initial check performed after a new software build is created.
Like right after the developers compile everything?
Usually, yes.
Yeah.
It doesn't test everything deeply. It focuses on the most critical paths and core functionalities.
Just checking if the basics work.
Essentially, yes. The goal is to quickly determine, is this build fundamentally stable enough to even bother with more detailed testing?
So it's like, does it catch fire immediately when you turn it on? Hence, smoke test.
That's the idea behind the name. If the smoke test fails badly, the build might be rejected immediately, saving everyone a lot of wasted effort trying to test something fundamentally broken.
Smart. Okay, what about sanity testing? Sounds similar.
It is similar in that it's also usually done post-build and is relatively quick, but it's typically more focused than a smoke test.
Focus on what?
Sanity testing often checks specific new functionality that was just added, or maybe a particular bug fix.
Okay.
And crucially, it also quickly checks the effect of that change or fix on the closely related areas of the application. It's a quick check. Did this specific change work, and did it break anything obvious right next to it?
Got it. So smoke is broad. Is it basically okay? Sanity is narrower. Did this specific change work and not cause immediate chaos?
That's a good way to think about it. Then there's end-to-end testing.
End to end. That sounds comprehensive.
It is. This type of testing isn't just about individual functions or modules. It's about validating entire workflows or processes from the very beginning to the very end, often simulating a real user journey.
Like from logging in, searching for a product, adding it to a cart, checking out, and getting a confirmation. The whole 9 yards.
Exactly that kind of scenario. It helps uncover issues with system interfaces, complex dependencies between different parts of the application.
Making sure data passes correctly all the way through.
Yes, ensuring data integrity across the entire system flow. It's really important for complex applications.
Okay. And one last set I wanted to ask about. Alpha, beta, and gamma testing. These sound like stages.
They are typically stages, often related to software releases. Alpha testing is usually an early stage,
Stand by.
often conducted in-house by developers, internal QA teams, maybe product managers, sometimes dedicated testers or even external teams acting as if they were users, but still in a controlled environment. It's about finding bugs early.
Okay. Internal focus. Beta testing.
Beta testing is when you release the software to a limited number of actual real-world end users before the official release.
So real people using it in their own environments.
Yes, exactly, on their own computers with their own data. The goal is to get feedback on usability, performance, and find bugs that only show up in diverse real-world conditions. Think of public betas for apps or games.
Right. I've definitely participated in those. And in gamma testing, I haven't heard that one as much.
Gamma testing is less common, or maybe just less talked about. It's typically a final check performed right when the software is considered ready for release, often focusing on specific requirements or security checks.
How's it different from beta?
It usually involves fewer testers than a beta, perhaps just key stakeholders, and often happens right before the launch, sometimes skipping extensive in-house testing activities at that point. It's like a final go-no-go check against critical release criteria, often at the ultimate user's location.
Okay, interesting. So we've talked about all these meticulous testing levels, types, techniques. It sounds incredibly thorough.
The aim is certainly thoroughness.
But here's where it gets a bit, well, philosophical maybe,
Okay.
and kind of fascinating. Despite all this effort, bugs still slip through, right? We all experience them.
Absolutely. And that leads to a fundamental concept, the inherent impossibility of truly exhaustive testing.
Impossible. Why?
Well, this impossibility isn't really a failure of testing, it's just a fundamental truth that shapes the whole field of software quality. There are two main reasons. First, software specifications themselves can often be subjective, ambiguous, or incomplete. People interpret requirements differently.
So the target isn't perfectly clear sometimes.
Exactly, but maybe more significantly, even with clear specs, most non-trivial programs have a mind-boggling, potentially infinite number of possible inputs, outputs, and execution paths.
Infinite. Really?
Think about all the possible combinations of data you could enter, the different sequences of clicks, the different environments it could run in. Testing every single one is just practically impossible in any reasonable time frame or budget.
Wow. So you can never prove a program is bug-free.
Correct. Testing can show the presence of bugs, but never their absence. It means we're not aiming for absolute perfection, which is unattainable. We're aiming for intelligent risk management. Finding the most important bugs, reducing risk to an acceptable level.
That's a really important perspective. So when something does go wrong, what's the terminology we use? We hear bug, but you mentioned fault.
Right. Technically, a fault is the actual defect or error in the code or system design. It's the underlying condition.
And the bug or failure is?
The failure is the observable incorrect behavior caused by that fault when the software is executed. So the fault is the root cause. The failure is the symptom you see. People often use bug loosely for either.
Gotcha. So when a tester finds one of these failures, indicating a fault,
Yeah.
what happens next?
They create a bug report. This is a really critical document.
Well, go ahead.
It's a detailed record of their observations for the developers. It needs to clearly outline the problem, describe the environment it happened in, like the browser version, operating system.
All the context.
Exactly.
Back.
Specific steps to reproduce the problem reliably, that they expected to happen versus what actually happened. And often they might suggest potential causes or even resolution steps if they have an idea. Clarity is key.
And within that bug report, I know there are two really crucial terms for deciding what gets fixed first: severity and priority. They sound similar but aren't, right?
They are absolutely distinct, and understanding the difference is vital. Defect severity relates to the technical impact of the defect on the application.
How bad is the bug, technically?
Is it crashing the whole system? That's high severity. Is it just a minor typo in some obscure help text? That's low severity. It measures the degree of impact.
Okay, impact. And priority.
Defect priority is about the business urgency. How quickly does this defect need to be fixed? This is often determined by product managers or business analysts, not just testers.
So a bug could be low severity but high priority.
Definitely. Imagine a typo, but it's the company logo spelled wrong on the main landing page.
Ouch. Low technical severity maybe, but super high business priority to fix immediately.
Exactly. Conversely, you could have a high severity bug, like a rare crash condition that only happens under very specific, obscure circumstances.
But it might get a lower priority if it affects very few users or there's an easy workaround.
Precisely. Severity is technical impact. Priority is business urgency.
That's a great distinction. Okay, so a bug gets reported, prioritized. Then what? Is there a standard process?
Yes, generally there's what's called the defect lifecycle. It's not just a single term, it's a workflow, a series of states or phases a defect goes through.
Like from birth to death?
Sort of. It starts when it's discovered by the tester, maybe status new. Then it gets assigned to a developer. The developer fixes it, fixed or resolved. Then it comes back to the tester to retest. Ready for retest.
And if the tester confirms it's fixed?
They might mark it verified or closed. If the fix didn't work, they might reopen it, sending it back to the developer. There can be other states, too, like deferred, if it won't be fixed now.
So it provides transparency and structure to the whole bug-fixing process.
Absolutely. Everyone knows the status of each reported issue.
Now, what about when things, get missed? I've heard the term bug leakage.
Yeah, that's the one testers don't like to hear. Bug leakage is exactly what it sounds like. It's when a bug is identified by the end customer or user after the software has been released.
Meaning it leaked through the entire testing process.
Exactly. It was missed by the internal testing team. It happens given the impossibility of exhaustive testing, but the goal is always to minimize leakage.
And what about defect cascading? That sounds potentially messy.
It can be very messy and make the debugging really hard. Defect cascading is when one initial, perhaps unnoticed, defect triggers a chain reaction, causing other defects or failures to appear elsewhere in the application.
Like dominoes falling?
Kind of. You might see a failure in one part of the system, but the root cause, the original fault, is actually somewhere completely different and earlier in the process. It makes pinpointing the original issue incredibly challenging because the symptoms are far removed from the cause.
Wow, that sounds like a nightmare to track down.
It definitely can be. It highlights why fixing bugs early is so important.
Okay, so stepping back to the tester's role. Practically speaking, when they encounter a bug, what are the key actions they take?
Well, first, as we said, meticulously log it in a bug report with all the details. Clarity and reproducibility are paramount. Then, ensure it gets assigned and communicated clearly to the relevant developer or development team. Proper tracking is essential.
Okay.
Once the developer provides a fix, the tester needs to retest that specific issue thoroughly to verify the fix actually works.
Just checking the original bug.
Checking the original bug, yes, but that's not always enough. The final crucial step is determining the need for regression testing.
Ah, regression testing. What's that again?
That means running a broader set of existing test cases, often automated, on the areas potentially affected by the fix. The goal is to ensure that the fix hasn't inadvertently broken something else somewhere else in the application.
Making sure the fix didn't cause regression.
Exactly. It's a critical step to maintain overall stability.
Okay, this is great. We've covered the process, the techniques, the bugs. But let's talk strategy. Beyond the nitty-gritty of finding individual bugs, what are the bigger picture considerations in software testing? How do you make it a real craft?
That's a great question, because it really is more than just finding bugs. It's about building confidence and quality. One key aspect is writing truly effective test cases in the first place.
What makes a test case effective?
Well, it starts way back with really understanding the client's needs, not just the technical specifications on paper. What problem are they really trying to solve?
Empathy for the user.
Yes. Then, ensuring your test cases collectively cover all the requirements, functional, non-functional if applicable, UI consistency, compatibility across different browsers or devices.
Being comprehensive.
Right, but also efficient. Avoiding pointless repetition. Setting clear priorities for your tests, which ones are most critical.
Focus on the important stuff.
And finally, using simple, clear, unambiguous language in the test case description and steps. Anyone should be able to pick it up, understand it, and execute it correctly.
Good communication, basically. Okay, another big strategic question. Manual versus automation testing. Is one better?
The classic debate. The real answer is, it depends. Neither is universally better. They have different strengths and weaknesses.
Okay, so what are the advantages of sticking with manual testing sometimes?
Manual testing often wins on cost-effectiveness for, say, short-term projects, or very exploratory testing where you don't know what you're looking for yet.
Right.
It provides that invaluable human end-user perspective. A person can notice subtle usability issues or visual glitches that an automated script might completely miss.
Like awkward layouts or things that just feel wrong?
Exactly. It's generally considered more accurate for GUI testing visual aspects, look and feel, accessibility nuances. And frankly, it's often easier for new testers to get started with manual testing. It's also good for tests that change frequently or are only run once.
Okay, so it definitely has its place. What about automation testing then? What are its big wins?
Automation really shines when you need efficiency and repeatability at scale. Its biggest advantage is supporting frequently repeated test cases like regression suites.
Running the same tests over and over after every change?
Exactly. It's great for testing large matrices of data combinations. You can run tests in parallel across multiple machines or environments, and critically, you can run them unattended overnight, for example.
Freeing up human testers for more complex tasks.
Precisely. The best strategy usually involves a smart, pragmatic blend of both manual and automation, leveraging the strengths of each.
Makes sense. Now, in modern software development, we hear a lot about Agile. How does testing fit into Agile methodologies? Is it different?
It is quite different in philosophy and practice. Agile testing isn't really a separate phase done at the end. It's an integrated part of the development process.
So testing happens alongside coding.
Yes, ideally, testing and coding occur almost simultaneously in short cycles or iterations. The focus is on evaluating the software continuously from the customer's perspective.
More collaboration.
Huge emphasis on collaboration between testers, developers, and business stakeholders. And it thrives on continuous customer interaction and feedback to guide development and testing efforts. Quality is built in, not inspected at the end.
That sounds like a much more integrated approach. What about risk-based testing? Is that related?
It can be used within Agile or other methodologies. Risk-based testing is all about being strategic and prioritizing your testing effort based on risk.
focusing on what's most likely to break or cause the biggest problems.
Exactly. You identify the areas of the application that carry the highest risk. Maybe they're the most complex, the most critical to the business, or have historically had the most bugs.
And you test those areas more thoroughly.
Yes, you allocate more testing resources and rigor to those high-risk areas. It helps you decide when and how to implement testing most effectively, ensuring you have measures in place to handle risks in the most critical parts first. It's about maximizing the value of your testing effort.
Being smart with limited resources. Okay, another acronym I've seen is PDCA cycle. Plan, Do, Check, Act. How does that fit in?
The PDCA cycle, also known as the Deming cycle, is a fundamental framework for continuous process improvement. It's applicable everywhere, including software testing.
Okay, break it down. Plan.
Plan your testing objectives. What do you want to achieve with this testing cycle? Define your strategy, resources, test cases.
Yes.
Execute the plan. Carry out the tests as designed.
Check.
Analyze the results. Compare the actual outcomes against your plan and expected results. Identify defects. Gather metrics.
And act.
Act upon what you learned in the check phase. If processes aren't working, improve them. If tools need changing, change them. If requirements were misunderstood, clarify them. Then you feed these improvements back into the plan phase for the next cycle.
So it's a loop for constantly getting better at testing.
Exactly. Continuous improvement is the goal.
Finally, what happens right at the very end of a testing effort? Is there a wrap-up process?
Yes, there's typically a process called test closure. It's not just stopping. It involves specific activities and often results in a test closure report.
What's in that report?
It's a formal document summarizing everything that happened during the testing phase of the software development lifecycle.
Like a final summary.
Yes. It includes things like a detailed analysis of the bugs that were found and fixed, maybe error trends, aggregated metrics like the total number of tests executed, passed, failed.
Data for reflection.
Absolutely. And crucially, it usually includes a list of any known unresolved defects, their severity and priority, and any workarounds. It's vital for making informed release decisions, for project sign-off, for audits, and provides incredibly valuable insights for improving testing on future projects.
Wow. What an incredible deep dive that was. We've really covered a lot of ground.
We certainly have.
We've explored the foundational concepts, dug into the practical techniques, the tools, the different levels and types, and looked at those crucial strategic considerations behind functional testing.
Yeah, from simply defining what it is, all the way through that intricate dance of finding, reporting, and fixing defects.
And even touching on that fascinating challenge that, truly thorough testing is by its very nature impossible.
It's a complex field, but so vital.
And hopefully it's clearer now why this knowledge is valuable. Whether you're actively building software or you just interact with digital products every day, which is pretty much everyone.
Mm-hmm.
Or maybe you're just curious about how this digital world actually works and stays reliable.
Yeah.
Understanding functional testing gives you some vital insight.
Yeah, insight into the quality we expect from our apps and maybe an appreciation for the meticulous effort required to achieve it.
Absolutely. So, as we wrap up, maybe something to think about.
Yeah.
A final provocative thought for you, the listener.
Okay.
Given that inherent impossibility of testing a program exhaustively, completely, as we've discussed, what do you think is the single most critical safeguard? Whether it's a human process, an automated tool, a specific technique. What's the most important thing to ensure the software we rely on day in, day out actually works as expected?
CTS Academy.